Hello, this is part 2 of Unit 6, lessons 6.1 to 6.3 about confidence intervals for proportions. So if you haven't watched the first video yet, you should go and watch the first video to get all the ideas how we're going to do this process. All right, so we did an activity in class, and if you wanted to do this at home, you could, but basically it was this. We wanted to know what proportion of the time would a Hershey Kiss land on its base. So we took a cup full of Hershey Kisses and we shook them up and we poured them out and we measured the ones that landed on their base, like here in the picture, counted those out. I did that 10 times to get a sample out of 100 and got 34 out of the 100 times. So this is my p-hat value for my sample of size 100. Now, we had all kinds of numbers in the classroom. Somebody got 29%. I had somebody with 18, somebody with 43. So if you're helping a friend in the class or if you've done this, you're going to see that everybody's answers are a little bit different. Okay, but we're going to work with this p-hat value that I got, which was 34%. All right, so after we get that p-hat value, if we want to deal with this, we need to check the conditions for inference for proportion. So there's three things that we need to make sure of. So the first thing we need to make sure of is that our sample is representative of our population. So if you think back to our Beyonce activity, it was really important that we took a random sample, because when we didn't take a random sample, the data didn't end up in the right place, and they didn't pile up in the right place, didn't give us the right value. So in our case here, we didn't technically take a random sample. I mean, I went to Walmart and grabbed these Hershey Kisses off the shelf. There was no randomness. We didn't randomly select them. So we can't count on the random sample to give us the representation. So we have to ask ourselves, is it reasonable that these Hershey Kisses are representative of all Hershey Kisses? And so we decided that yes, that was reasonable, that these weren't significantly smaller or larger or way less or differently shaped. They seem to be pretty representative. So if your problem ever doesn't state that it's a random sample, this is something that you could use as an assumption. You could say, let's assume that the sample is representative of the population. That's reasonable to assume. Now, there's sometimes when it wouldn't be reasonable to assume. For example, it wouldn't be reasonable to assume that a classroom full of AP statistics students could represent the math skills of all Avon High School students. That wouldn't be a reasonable assumption, because we would figure that the AP statistics students would have higher math skills than some of the other students in our building, and so overall our math skills would be higher. Just like we would not expect that a random sample of elementary school girls could represent all girls in the United States. We would have to look and say, well, what about, does it make a difference that they're from Hendricks County, or does it not make a difference? So we would want to look back and forth, be really careful about this. If you're ever not sure and you think maybe this isn't a good idea, you could say, yes, this is reasonable to assume, but I proceed with caution. All right. Now, the other thing we have to do is that we are sampling without replacement. So is it reasonable to assume that 100 is less than 10% of all Hershey Kisses? That seems very reasonable. Okay. Is the sampling distribution of p-hat approximately normal? Now, we don't know what p is. We have a guess. I got 34% in my sample, so I could use that as an estimate, and that's basically what I'm going to have to do. So I'm going to hope that p-hat is close enough to p that when I take my n times p-hat and n times 1 minus p-hat, I end up with numbers that are bigger than 10. Now, if your answer is really close to 10, that kind of makes us a little nervous, because we know that p-hat and p are not necessarily the same. But as long as you're significantly larger than 10 in both of these counts, it should be safe to say that even though we don't know p, if it's close to p-hat, we should still have an approximately normal sampling distribution. So I actually checked this: 100 times 34% and 100 times the failure rate, 66%. And I got those counts. All right. Now, to construct a 95% confidence interval for proportions. Okay. So we're going to construct something called a one sample Z interval for proportions. And these are all going to have different names as we work along. So the first part is how many samples we take, either one or two. Are we have one group, or are we comparing two groups? Then we're either going to have a Z interval or a Z test in this chapter. We're dealing with confidence intervals today. Later on in the chapter, we'll deal with hypothesis tests, and so you'll have a choice between a Z interval and a Z test. And then at the end, we've got this for proportions. In our next unit, we'll have something for means as we go through here. Okay. Now, on your AP Statistics formula sheet, you are going to see this formula right here. Confidence interval is the statistic plus or minus the critical value times the standard error of the statistic. This is on the front page of your formula sheet under this heading that says sampling distributions and inferential statistics. It's the second one down right there on the formula sheet. That's not something you have to have memorized. So again, remember what this is saying. Statistic, that's the number we get from our sample. I'm going to find a proportion plus or minus the critical value. The critical value is the number of standard deviations you want to go out to trap a certain percentage of all values. So that was that z-score. And then it says times the standard error of the statistic. And we didn't talk about that last time, but we did say it's about the standard deviation. Like you want to go out about 2 standard deviations to trap 95%. So let's get going on this. So for our example, our statistic, our p-hat value was 34%. So that's the statistic. Our critical value, because we want a 95% confidence interval, we want the z-score that traps 95% of the normal curve in between plus or minus z. And we figured out in our last video that that was 1.960. Now, sometimes this is referred to as z sub 0.95, that'd be a 95% z, or z star, you might see these notations. And again, that's because 95% of the normal distribution is within plus or minus 1.96. And if you don't know where that came from, watch the previous video. You can also get it off of the table, the T table, it's on the very bottom, or you can calculate it in your calculator. And then finally, the standard error of the statistic. Now, we have this issue that when we go to our formula sheet, on the formula sheet, we have this formula for standard deviation, but the standard deviation of the sampling distribution uses p. We don't know p. That's what we're trying to find. All we have is a p-hat from a sample. That's 34%. So standard error, and you can see even says that on the formula sheet, standard error of the sample statistic is the exact same formula as the standard deviation formula. The only difference is that it uses p-hat instead of p. So we're using, just like in the n times p formulas, we're using the p-hat value in place of p because we don't know what that one is. So the idea here with the notation, remember we use Greek letters for population and English letters for samples. So sigma of p-hat is the one that uses p, which is a population characteristic, whereas s, that's the standard deviation estimate here of p-hat because it uses the sample data. All right, so to find that standard error, we're going to use this formula, the standard deviation formula, but it's been subbed in for p-hat instead. I'm going to put in 34% times 66% divided by 100. I take the square root. That gives me about 0.047 for my standard error. All right, so I know that the statistic is 0.34, the critical value is 1.96, and the standard error is about 0.047. So I'm going to sub those into my formula, 0.034 plus or minus 1.96 times 0.047. All right, when I do 1.96 times 0.047, I get 0.092. I'm going to go up and down by that amount. This is called the margin of error, and I end up with 0.248 on the low end when I subtract and 0.432 on the high end when I add. So that is my confidence interval. That is the interval of plausible values for the thing that I was trying to estimate. This is like the Price is Right game where I slap the button and it places that red bar. I have got the red bar placed between 0.248 and 0.432, and I want to know, do I win the trip to Rome? All right, now to interpret this, I'm going to write this as a complete sentence, and I'm going to say, I am 95% confident that the true population proportion of Hershey Kisses that land on their base is captured by the interval 0.248 to 0.432. In other words, I believe that the truth is somewhere in this interval. Now, I could still be wrong because I'm only 95% confident. If I need to be 100% confident, I get a much wider bar that's probably not going to be as useful. Okay, so this is a confidence interval. So to construct a confidence interval, if you want to do a point grab and you want to get all the points available for you on that AP exam, here's my suggestion of what I would recommend that you do. Okay, so first off, at the beginning of every problem, you are going to identify what's the population, what's the variable, is it categorical or numerical. You need to get in the habit of doing that so that when we start throwing means and other things in, that you can identify which procedure is correct. So start to think about that now. And then you are going to panic. Now, panic is a mnemonic to help you remember the steps to do. Okay, you don't have to necessarily do all these steps in this order, but as long as you do, you should get everything you need. So panic. So the P of panic says, what parameter do you want to estimate and at what confidence level? So basically what this is asking you to do is define the parameter variable using words. I want you to say P, because we're talking about a portion, is the true proportion of Hershey Kisses that land on their base, of people who showed improvement after medication, of orange Skittles in the bag, okay? So we're going to define that in context. This is what we're trying to do, and you want to identify that confidence level as well. The next thing you're going to do is you're going to check the assumptions for the assumptions and conditions. So these are the conditions for inference. And if you can't, if they're not explicitly stated, then you're going to have to make some assumptions before you're allowed to move on. So the three things you need to check are, is it a random sample? Have I satisfied the 10% condition? And is it approximately normal sampling distribution? All right, so you have to show these being checked too. So for the random sample, you want to say, okay, is it a random sample? And if it doesn't say it's a random sample, then you're going to have to make an assumption. You can't assume it was random, but you can assume that the sample is representative of the population, much like we did with the Hershey Kisses. Okay, so I think so. To check for independence for all this, you need to make sure your data is from a random sample for a randomized experiment, because we want it to be representative of our population. The next thing is that 10% condition. We want to check to make sure we sampled a small enough sample that we have independence. Okay, so less than 10% of the population. And then I want to check to see if it's approximately normal. Now, normally we would check n times p and n times 1 minus p for proportions and see if they're greater than 10. The issue is, since we don't know p, we're going to use p hat, and we're going to hope that if the sample size is large enough, that that is going to give us enough evidence that we can support that this is approximately normal. All right, now the next thing we want to do is name that procedure. This is something that you're going to need to write down. This one is a one sample Z interval for proportions. And if you'll get in the habit of writing these down correctly, it can save you a lot of habit and be a good point grab later on. A lot of work can be saved. Okay, the next thing I want to do is find the interval itself. And basically what this is asking you to do is to do the math. This is the actual math step. Find the interval. So I'm going to take the point estimate plus or minus the critical value times the standard error of the statistic, or the statistic here is the point estimate. So for proportion, you're going to take a p hat plus or minus the Z critical value for the confidence interval times the standard error, which is just the standard deviation with the p hat values in there instead. This is going to give you two numbers. We have a lower bound and an upper bound then. A lower value for the confidence interval and an upper bound. And then finally, you're going to write the conclusion. You're going to write a complete sentence, and it's going to have this format. It's going to say, I am C% confident that the true parameter, in our case, the population proportion of, and you want to make sure you put it in context. You should reference the population of all Hershey Kisses, okay? And you should explain which side of the proportion you're looking for that landed on their base. Okay, be very specific, is captured by or is between that lower bound and upper bound. Now, just a real quick other vocabulary word here. The thing that happens after the plus or minus is referred to as the margin of error. So, for example, when we did the Hershey Kiss problem here, I had 0.34 was my statistic, 1.96 critical value, 0.047. If I multiply those two things together, I got 0.092. That 0.092 is referred to as my margin of error. So, it was 34% plus or minus about 9%. There's about a 9% margin of error here. Okay? All right, so let's do an example. Oh, and I've got the answer at the bottom due to my terrible PowerPoint skills. So for a project, a student randomly samples 182 other students at a large university to determine if the majority of students were in favor of the proposal to build a field house. He found that 75 students were in favor of the proposal. Construct a 95% confidence interval of the true proportion. All right, so the first thing I'm going to do is I'm going to pick out the information from the problem. We took a sample of 182, that's N. 75 were in favor, that's the number of successes if we're counting people in favor. And it says 95% confidence here, so that's my confidence level. All right, so P, parameter. All right, the true proportion, so P is the true proportion of students in favor of the field house. That's what our lowercase p is. I'm going to do my assumption here. What are my assumptions? Is it a random sample? Yes, it is, because it was stated. So I'm going to write that down. Random sample, stated. I got to check the 10% condition. Is 182 the sample size? Less than 10% of all students. Now, I don't know how many students there are, so I'm going to write that generically in context here. All students. But it does say it's a large university, so that seems pretty reasonable. All right, the next thing I need to do is I need to check to see if the sampling distribution is approximately normal. So I want to check those expected counts. Now, I do not know p hat. It was not given to me, so I have to find it. So p hat was 75 out of 182. That's about 0.412. So I'm going to take, is 182 times about 41% is about 75. That's bigger than 10. 182 times 59%, that's about 107. That's greater than or equal to 10. Now, that's great, and that has to be shown. You got to show those numbers subbed in there, show they're bigger than 10. But remember, the reason why we're doing that is to show that the sampling distribution is approximately normal. And because it's approximately normal, that means that when we talk about this 95%, we can use that Z 1.96. Those probabilities associated with Z only work in a normal distribution. So if you don't have a normal distribution, we can't count on Z to tell us how far away to go to be a certain level of confidence. All right, so name that test. This is a one sample Z interval for proportions. One sample Z interval for proportions. All right, next thing I want to do is the interval itself. So I'm going to take the statistic p hat 0.412 plus or minus the critical value. Now the critical value is 1.96 because we are 95% confident, and that's the Z that's going to trap that, times the standard error of the statistic. In other words, we're going to have standard deviation, but we are going to use our p hat value in there instead. So 0.412 times 0.588 divided by 182. Now, you can do this all in one step in your calculator, or you can do this side first. Just make sure you use enough decimal places that it has some degree of accuracy. Okay, so I did the right side here first in my calculator. I got 0.072. That's the margin of error. I'm going to add and subtract those two values and get my confidence interval of 0.34 to 0.484. Okay, so conclusion. I am 95% confident that the true proportion of students in favor of the field house is between 0.34 and 0.484. All right, so that is my complete answer. Now, the reason why we want to do all these steps of panic is because this is going to help us get all the points available to us on the AP exam. Now, traditionally in years past, and it may change, it's always subject to change, these problems usually have about 4 parts that are graded. Okay, so the first EPI that gets graded is usually for the P and A part of panic. It's for that context and for the checking of the assumptions properly. Okay, so just for the P and the A, that's usually the first part that gets graded. The second part that gets graded is the N and the I step, where you show the name of the procedure or the formula for the procedure, and you actually find the interval itself. So that's the second E. The third E is for that conclusion sentence in context. So you get like an E just for doing that correctly. And then a lot of times there's a fourth E available that's based on some sort of, okay, now look at this and tell me about it situation. So in the original problem, it says that they wanted to determine if a majority of students were in favor of the field house. Now, if I had to answer, is the majority of students in favor of the field house? Based on this confidence interval, I'd have to say no. Because if the majority of students are in favor, that means that our true proportion is more than 50%. And if you look at our confidence interval, we think the true proportion is somewhere between 34 and 48%. But even if it's anywhere in that interval, that's going to be less than 50%. So it doesn't seem plausible that the true answer could be more than 50% based on this confidence interval. Okay, let's run through one more very quickly here. So the city council became concerned about the trend toward exclusion of renters with children in apartments within the city. Like my parents live in an apartment. You had to be 55 or older to live in their neighborhood and live in those apartments. To determine the extent of this problem, they selected a random sample of apartments and determined for each whether or not children would be permitted. In 37 of the 250 sampled apartments, the apartments prohibited renters with children. All right, estimate the proportion of all apartments in the city that exclude renters with 90% confidence. So that word estimate tells me that we're doing a confidence interval here. I want to estimate a value. I don't know what the exact number is, but I'm going to get a range of values in this case. A couple of the things I can pick out from this problem. I know that 37 out of the 250 gives me a p hat from the sample of 37 out of 250, which is about 0.148. Now, if you ever have to round these decimals, your answers could be slightly different from somebody who leaves it as a fraction. So just remember to leave enough decimals and show your work so that that's not an issue. The other issue is that this says 90% confidence. So you're going to have to find the z-score that traps 90% of the curve between it. So in our case, you could do that in your calculator. If you've got 90% in between, that's 5% on either side. You could run a little inverse normal and get that 1.645. Or you could use the number at the bottom of that t-table to get that confidence level. All right, so we have our z there. So I'm going to start with p. I'm going to define the parameter. So the parameter is the true proportion, the proportion of all apartments that exclude children. Okay, the true proportion of apartments that exclude children. Check the assumptions. It is a random sample. I know because that was stated. 250 is the sample size. Is that less than 10% of all apartments? That seems reasonable. I don't know how many apartments in the city, but it's reasonable to assume that that would be true. And I have to check to see if it's approximately normal. So 250 is my sample size times the p hat value, because I don't know p. That's 37, which is greater than or equal to 10. If I do the other side of that, the failure rate's going to be about 85% based off of that, about 15% there. That gives me 213. Both of those are bigger than 10, so I know my sampling distribution is approximately normal. All right, I'm going to name that test. We want a one sample, because that's how many we took, z interval, because we're talking about a normal distribution here, for proportions. Proportions are what we're trying to deal with, okay? So p hat, that's my 0.148, plus or minus the critical value for z, 1.645, times the square root of the 0.148 times 0.852 divided by 250. I'm going to compute that. That right side there after the plus or minus comes up to about 2%. Gives me a final answer of 0.126 to 0.170. All right, so to conclude, I am 90% confident this time, 90%, because that's how far we went out to trap, that the true proportion of apartments that exclude children, there's that context, is captured by or somewhere between 0.126 and 0.170. All right, now there is a follow-up question on this problem, and it says, the housing coordinator claims that the proportion of apartments that prohibit children is greater than 10%. Does the confidence interval you constructed above support this claim? All right, so the confidence interval was 0.126 to 0.170. Is this help us say that we think it's greater than 10%? And I think so, because we believe that the true proportion is somewhere between about 13% to 17%. That entire confidence interval is bigger than 10%. So it's reasonable to conclude that the true percentage is also above 10%. Okay. All right. Now you can use your TI-Nspire, do a little bit of heavy lifting on these problems. Okay. I would recommend that for a little while you continue to use the formula. You need to know how to use the formula and how to set it up, because that's going to make you a better statistician, and also you need it for like multiple choice questions, whatever. But you can do some careful work, and I'm going to talk about that more in class, and can use your calculator to do this. So here's the way it works. For example, you randomly select 100 students and 45 tell you that their favorite color is yellow. You can create a 99% confidence interval for the proportion of students who prefer yellow. So if this was a multiple choice question, what I would probably do is I would identify these important pieces. Sample size was 100, 45 said yellow, and I want a 99% confidence interval. Then I would open my calculator and I would go to a calculator screen. I'd press menu, statistics, confidence intervals, number 6, and I want number 5, a 1 proportion z interval. Okay. Now, it's going to ask you for X, which is the number of successes, which in this case is 45. The sample size is 100, and then you're going to have to type in, because it defaults to 0.95, the 99%. Okay, when you do this in your calculator, you get a little report back, and it's going to say C lower and C upper. And that is going to be what you use for your confidence interval. So that gives me 0.322 up to 0.578. Okay, you can also see it's 0.45 plus or minus that margin of error there if you think that would be useful. All right, now if I said 38% of 252 students said their favorite color was yellow, what would the 95% confidence interval for the proportion be? This is a little bit of a problem because that X is not a percentage. That X is a raw count. It's a how many out of 252. And when you take 38% of 252, you end up with 95.76. Now, if you put 95.76 in that spot for X in your calculator is going to lose its mind. It's going to go, what are you doing? Because X is a count. just like n, and so it has to be a whole number, And so what you want to do is for x, you want to use the nearest whole number, 96, in that spot. If you type in 95.76, you're going to get domain error. It's not going to like it. So you want the nearest whole number. So you type in 96 and 252, and at 95% confident, and it's going to give you your answer, 0.321 times 0.441. All right, there are a few other things we need to talk about with confidence intervals, but I'm going to do that in the next video. So this all about constructing and going through the process. Okay, the one before this all about the theory behind it and how we get to this idea.